Hello, welcome to 19th lecture of two-phase flow and heat transfer course. Today's topic we will be discussing about solid liquid flow. Okay. So, at the end of this lecture we will be understanding the following topics. We will be understanding different regimes of solid liquid slurry flow and their corresponding conditions for occurrences. We will be explaining methodologies for calculation of pressure drops inside a pipe carrying slurry flow. We will be seeing in laminar and turbulent regime what will be the slurry pressure drop. We will be expressing the pressure drop for non-Newtonian slurry, and finally we will be showing you that how heterogeneous slurry can be tackled and its related pressure drop can be calculated. In this context we will be introducing two layer model. Okay. So, let us first see what is this solid liquid and how that can be characterized. Solid liquid flow, mainly it is classified as slurry flow. Okay. So, in slurry you will be finding out suspension of solid particles, okay, in liquid. Okay. Now, the mixture of solid and liquid can have different formats, that means it can be homogeneous mixing, it can be heterogeneous mixing and so on. And overall whenever it is homogeneous mixing, there can be fluid properties, dependent on that we can classify this one as Newtonian and non-Newtonian slurry. So, let us first start to understand that what are the different characteristic parameters for slurry flow. So, first we will be seeing what is slurry flow velocity. So, in case of slurry flow velocity, we write down the velocity as um. So, which signifies that the mixture velocity, remember this velocity is for a homogeneous mixture. Okay. So, this velocity can be characterized as volumetric flow rate of solid plus volumetric flow rate of the liquid divided by the pipe cross sectional area. So, that means V dot S, which is the volumetric flow rate of solid, plus V dot L divided by A, that is your flow velocity, slurry flow velocity. Okay. Immediately next we need to know what is the concentration of solid in the slurry. So, that concentration, solid concentration, we express in the form of alpha S. So, alpha S is the solid concentration, that can be written as obviously the ratio between the solid flow rate divided by the overall flow rate. So, here solid flow rate is V dot S and overall flow rate is V dot S plus V dot L. Okay. So, this is actually your solid concentration alpha S. In a similar fashion we can define the mass fraction of the solid. So, mass fraction means here solid concentration is in the term of the volume fraction. So, once we find out the mass fraction of the solid, then we will be finding out that we have to multiply this alpha S expression with their respective densities. Okay. So, you will find out that Cs is nothing but here we had V dot S. So, it will be V dot S into rho S to get the mass of the solid divided by whole mass. So, whole mass will be nothing but rho S into V dot S plus rho L into your V dot L. Okay. Now, little bit of modification of this one, if I divide this one with V dot S, the whole equation if I divide, then you will be finding out that we can replace this volumetric flow rates in terms of your alpha. So, we can write down alpha is your nothing but your solid concentration previously explained. So, we will be finding out that it will be this expression will turn out to be rho S alpha S divided by rho S alpha S plus 1 minus alpha S into rho L. Okay. So, just division of this V dot S by V dot S plus V dot L will be giving you this one. So, denominator and numerator you divide it by V dot S by V dot L. Okay, next if we try to find out that what is there at the bottom side of this solid concentration, this we can define as mean slurry density. Okay. So, rho m mean slurry density will be equals to alpha S solid density multiplied by your alpha solid density is rho S and alpha S is your solid concentration plus 1 minus alpha S, which is actually your liquid concentration multiplied by rho L. Okay. Next, let us see that while we are having slurry flow, what different flow regimes are possible. Okay. So, we will be starting with a very low liquid velocity, we will be starting with the velocity contour over here. So, what we will be finding out that slurry flow regimes, depending on the dispersion of the solid in the liquid, can be classified into several categories. Okay. Starting from this one, which is homogeneous flow. Here you can see inside the pipeline we are having homogeneous dispersion of the solid. Okay. So, everywhere the solid concentration will be more or less similar. Okay. So, you see over here particles are well dispersed. Okay. So, if we try to plot its solid concentration, we will be finding out solid concentration across the pipeline is a constant curve. So, that means everywhere we are having same solid concentration alpha s. So, that is characterization of this homogeneous flow. Okay. Next, if the solid concentration increases, then you will be finding out that some amount of solid is getting settled down. Okay. So, we go for different solid concentration at different radial location. So, that is called heterogeneous flow. In case of heterogeneous flow in the schematic, I have shown you over here at the lower side of the pipeline you can find out more amount of alpha s or solid concentration, whereas in the upper side we are having very low amount of solid concentration. So, if you find out the solid concentration curve along with the radial direction, so you will be finding out that it is increasing whenever we go down. Okay. Next, let us see whenever we are having flow with moving bed. So, in this case you will find out that there is some sort of deposition on the bed of the pipeline. Okay, at the bottom side of the pipeline the solid has deposited and formed a bed, and that bed is actually moving along with the flow. Okay. So, here you will be finding out, and this bed whenever it is moving you will be finding out this is very thin in nature. That is why it can be transporting with the overall flow. So, you will be finding out over here that though we are having precipitation or downfall of the solid particles, but along with the flow, carrier flow, liquid flow, we will be finding out this solid will be also transporting. Okay. So, if we find out the solid concentration, we will be finding out a curve like this. Here we are having overall moving particles, and here we are finding out that solid concentration is very high, but still that is moving. Okay. But it is characterized by a thin layer of this higher solid concentration. Okay. Next, we will be finding out still if we increase the solid loading, then we will be finding out we are getting flow with stationary bed. Now, what will happen? You will find out though there is a solid bed at the bottom of the pipeline, but due to its thickness you will be finding out that the liquid incoming slurry mixture will not be able to transport the whole amount of solids. Okay. So, you will be finding out that this bed is more or less stagnant or stationary. Okay. But if we try to plot the solid concentration, we will be finding out that it is having a very high concentration at the bottom, which is stationary actually, and here we will be having moving slurry. Okay. So, you can find out the thickness of this one, okay, with the higher concentration is far higher compared to this one where we are having lower one. So, these four regimes we can see starting from homogeneous, heterogeneous, your moving bed and stationary bed in case of your slurry pipeline. Let us try to see now how we can characterize these flow regimes depending on the velocity, mean velocity of the slurry and the particle diameter, because these are the two important parameters on which the regime will be depending. So, let us see over here. So, here you see in the abscissa we have plotted the mean slurry velocity, and in the ordinate we have plotted the solid particle size dp. So, you can find out over here whenever the liquid velocity is actually increasing, very high liquid velocity, or you can say at lower size of the solid particles, always we will be getting homogeneous mixture of the solid and liquid, which can be characterized as homogeneous flow. Okay. So, that means there we are having well dispersion of the solid particles and the carrying liquid. So, if the particle sizes are small, then we can find out that it is having a homogeneous mixture. On the other hand, if the flow velocity is high also, then also we will be getting that it is having homogeneous mixture. Next, just if you increase the solid particle size, that means the particles, if those are getting bigger, then there will be role of gravity which will be allowing the solid particles to fall down, and you will be finding out that there is some sort of non-homogeneous mixture, okay, or we can say heterogeneous flow, okay, inside the pipeline. So, this heterogeneous flow actually occurs for larger size of the particles, okay. Now, if we go for further higher particle sizes, then you will be finding out that not only the heterogeneous flow is actually balancing that one, you will be finding out there is deposition of the solid or the bed of the pipeline, and you will be finding out we are having flow with moving bed, okay. And whenever the liquid overall mixture velocity is reducing further, then you can find out that the bed is getting thicker and thicker, and finally the bed will become stationary, and we will be obtaining flow with stationary bed, okay. So, flow with stationary bed happens at very high particle size or very low mixture velocity, okay. Now, let us see how this homogeneous flow can be tackled rheologically, okay. That means how to find out the mixture properties. Already I have shown you the density, how to find out the mixture density, okay, for solid liquid flow. Here I will be showing you how to find out the mixture viscosity, because these are two important rheological parameters we need to take care of. So, here let us see a rheological model. So, first I will be showing you for a Newtonian slurry, that means homogeneous, but still the fluid is behaving as Newtonian, that means your shear stress and strain, those are proportional to each other. So, we can write down in that in that case that your viscosity follows a model, famous model called Thomas model. So, Thomas has given this model for finding out the viscosity in 1965. What he proposed? He proposed that mu r is actually relative viscosity of the mixture and the liquid. So, mu r is actually mu m by mu l, okay. That is equals to 1 plus 2.5 into alpha s plus 10.05 alpha s square plus 0.00273 e to the power 16.6 into alpha s. So, that means this relative viscosity is actually a function of your solid loading alpha s, okay. So, once we find out what is the loading, then we will be getting the value of the mu r, and once I know the value of carrying liquid viscosity, which will be a pure fluid, we will be getting what is the mixture viscosity over here, okay. So, finding out rheology is not that much difficult now. So, next as we have done in case of your gas solid pipeline, here also let us do the same thing, find out the pressure loss, okay, whenever we are having slurry flow, and let us consider that the pipe is having a straight section. So, let us not go for critical things like bend or something T joint or something like that. Let us consider we are having a straight circular pipe, and we are finding out the pressure loss. Now, let us see, by the way, if we are doing it for some bend section or something like that, then we will be finding out a function of the pressure drop will be coming over here, which is called PFT, which we have mentioned over here as pressure drop due to pipe fittings. So, pipe fittings can be bend, pipe fitting can be T junction or something like that. So, those empirical relations are already there through which we can find out the pressure drop in case of the pipe fittings. So, I will not be going in detail of the pipe fitting pressure drop, but let us see that what are the other parts. So, other parts, as we know that in the steady slurry flow we will be having the frictional pressure drop, as well as we will be having the buoyancy pressure drop or gravitational pressure drop. So, gravitational pressure drop is very simple. So, we know the mean slurry density, already I have shown you how to calculate. So, that will be alpha s into your rho s plus 1 minus alpha s into rho l. So, once we know the mean slurry density multiplied by G, and then the potential head what the pipeline is actually occurring inside the pipeline it is occurring. So, that will be giving me the potential head or buoyancy head, okay. So, we are mainly interested in the pressure drop due to friction, so PF. So, all we know that is that pressure drop due to friction PF is equals to F into 4 by 4L by D into rho m um square by 2. Okay. So, you see in this expression which is coming from fluid mechanics. So, all other parameters will be known including the rho m and um, okay, but only unknown will be f. So, main target of this derivation is to show how f can be calculated. So, let us see how f can be calculated, but before going that let us try to find out what is the mixture volumetric flow rate. First we will be starting with the laminar one, okay. So, then quickly we will be going for the turbulent one. So, first we will be showing with the laminar slurry. So, in case of laminar slurry we will be finding out V dot m, which is the mixture volumetric flow rate, is nothing but 2 pi r Vr into dr. So, Vr is the, let us say, radial at a particular radial location, what is the axial velocity. So, this will be multiplied with 2 pi r into dr. So, 2 pi r is actually the circular arc and multiplied by dr is actually infinitesimal small circular ring, and if we integrate it from 0 to d by 2 pipe diameter, then we will be getting the overall pipe area multiplied by Vr, which is dependent on the radial location, we will be getting the volumetric flow rate V dot m. Okay. So, if we do the integration by parts, because here we are having r, here also V is a function of r, then we get Vr integration of 2 pi r dr minus dv dr integration of 2 pi r dr into dr. Okay, limit stays over here from 0 to d by 2. Now, if you come over here for the first term, you see this is coming as v by Vr into 2 pi r dr comes out to be pi r square, and the limit is 0 to d by 2. Now, interesting thing over here is that Vr will be becoming 0 at d by 2, and at r equals to 0 the whole expression gets 0. So, at upper limit and lower limit this expression will be vanishing. Okay. So, this goes to 0, but here in the other hand side you see we are having dv dr. So, dv dr is nothing but your strain. So, I can write down gamma dot, okay, and here 2 pi r dr integration of 2 pi r dr, this gives me pi r square, and overall dr remains over there with the limit of 0 to d by 2. Okay. So, if we go further, we can write down that this Vm is actually a function of your shear stress. So, let us see how we can do that. So, let us first balance the frictional force and the wall shear stress. So, already we have done this kind of analysis in case of your pipeline flow, gas liquid pipeline flow. So, pi r square into Pf, which is the frictional force, is actually equals to 2 pi r L. So, 2 pi r is actually your perimeter, and then L is the length of the pipe multiplied by the shear stress, wall shear stress tau. Okay. So, if you balance this one, you can write down tau is nothing but r by 2 Pf by L. So, what I can do, I can replace always tau in terms of r by 2 Pf by L. So, already we had over here you see gamma dot pi r square dr. So, what we can do, we can replace over here that what is the value of gamma dot over here. So, here we have you see from here if you find out what is the value of r will be 2L tau by Pf. So, we have given 2L tau by Pf whole square. So, this is gamma dot r square, and if you do the differentiation of r with respect to tau, you will be getting dr is equals to 2L by Pf into d tau. So, here I have written that one in place of dr. Now, once you simplify this one, you will be getting that V dot m is equals to minus pi 2 tau L by Pf whole cube, because here we have whole square and here we have single Pf. So, it becomes whole cube, and then 0 to d by 2 inside the integration it is tau square gamma dot into del tau. Okay. Now, for the wall we know that r equals to d by 2, tau will be going to wall shear stress tau w. So, tau w can be written as, once again by following this equation, it can be written as d by 4 Pf by L. So, what we can do, this expression Pf I can replace using tau w. So, this comes out to be minus pi by 8 d by tau w whole cube, and then the integration 0 to tau w tau square gamma dot del tau, right. So, let us continue further. So, if you see in case of Newtonian slurry, we know laminar and Newtonian. So, we know that tau is equals to mu m into gamma dot. So, let us replace this gamma dot over here with this mu by tau, tau by mu. So, we will be getting something like this. So, tau cube mu m delta tau. Okay. Once we go for the integration, it gives me tau to the power 4 by 4 mu m, okay, and cancelling out tau cube and tau to the power 4, it gives me pi by 32 tau w d cube by mu m. Okay. So, ultimately V dot m we get, if we once again replace back this tau w with respect to P f. So, we will be getting pi by 128 d to the power 4 P f by mu m into L. Okay. You can get back the value of tau w also from this expression in terms of Vm. So, tau w comes out to be 32 mu m Vm divided by pi d cube. Okay. So, this is the expression for tau w and Vm. Okay. Then let us quickly calculate what is the friction factor. All of we know that friction factor tau w, friction factor F is actually your tau w by rho a mu m square by 2. So, little bit of simplification and putting the values of V dot m and tau w from here, you will be getting that this comes out to be 16 mu m by d rho m u m. Okay. So, ultimately it becomes 16 by mixture Reynolds number REM. Okay. So, this mixture Reynolds number will be following the density of the mixture and the viscosity of the mixture, right. So, if we go for the non-Newtonian version of this one, so here I have shown you 3 different non-Newtonian models: power law, Bingham plastic model and Herschel-Buckley model. So, all of we know from fluid mechanics that for power law tau is equals to Kp gamma to the power n, for Bingham plastic tau is equals to tau b plus eta b gamma to the power n, and for Herschel-Buckley this is tau h plus Kh into gamma to the power p. So, if we put all these things in the previous integration whatever I have shown you, ultimately you will be getting that this f is nothing but 16 by Reb into this non-dimensional number ratio, where you see we are having your Hedstrom number and Reynolds number over here into picture. Okay. Similarly, for power law we are getting Rep, which is nothing but your Reynolds number, and here this is the function which is involving the term n, which is the characteristics of this power law model. Similarly, for Herschel-Buckley you see we will be finally getting f is actually this term, where you see p is one parameter which is coming from the model, and tau h will be also coming over here because these are model parameters for Herschel-Buckley. Okay, let us go to next from laminar to turbulent. In case of turbulent flow, we will be finding out that the famous correlation, Churchill's correlation, can be used for finding out the friction factor. So, Churchill he has mentioned that F is equals to 2 into 8 by Re to the power 12 plus A plus B to the power minus 1.5 and overall to the power 1 by 12. Okay. Here A and B, these are actually given here like this: A equals to 2.457 ln of 1 by C to the power 16 and B is 37530 by Re to the power 16, okay, where C is nothing but dependent on the Reynolds number and the relative roughness of the tube E by D. Okay. So, once you know the friction factor, it is also necessary to get the mean velocity. So, Churchill has proposed that mean velocity um divided by u star, where u star is a slurry velocity. Slurry velocity can be written as tau w by rho m to the power half. So, that is equals to un by u star plus 11.6 into 1 minus alpha minus 1 minus of 2.5 into ln alpha minus gamma. Now, let us see what are these terms. So, un is nothing but mean velocity of the equivalent flow, okay, equivalent flow of the liquid. Okay. Then alpha is the rheological factor, okay, alpha can be found out for different fluids, I will be showing you. Gamma is reduction in mean velocity due to flattening central core. So, in case of non-Newtonian, you will be finding out there is flattening of the central core, so that gamma is taking care of that one. So, gamma can be written as minus 2.5 ln of 1 minus zeta minus of 2.5 zeta into 1 minus 0.5 into zeta, where zeta is nothing but tau y by tau w. Tau y is nothing but once again yield stress, can be found out from the materialistic properties, and alpha, whatever I have told here, the rheological properties or factors that can be that Churchill has proposed for different fluids, Herschel-Buckley, power law fluid and Bingham fluid, different functions of zeta and the rheological parameters. Okay. Then let us go to heterogeneous slurry. So, after this homogeneous slurry, all of we know that we will be having homogeneous slurry at a very high velocity. Then once the velocity decreases, we will be finding out that heterogeneous slurry comes. Then slowly further reduction will be giving you moving bed, then stationary bed, and at some point of time at very low velocity you will be finding out the pipe is totally plugged. okay, with solid. Okay. Now, here we have some typical boundary velocities which will be differentiating between homogeneous and heterogeneous and bed, okay, wherever the solid starts to drop down or settle down. Okay. So, let us understand what is UM1 and UM2. So, Newitt in 1955, Newitt et al. In 1955, they have given the idea what will be the UM1 and UM2. They proposed that UM1 will be 38.7 into GdVs, okay, to the power 1/3. So, this Vs is once again solid loading, and he has also proposed that UM2 can be written in terms of your density of the ratio of solid and liquid and some important factors K1, K2, K3, K4, K5, okay. And he has given this one for Newitt, he has given this one for particle diameter 1 micron, okay. So, he has proposed UM2 as this correlation, right, which is dependent on different Ks, 5 Ks and S, okay. So, what we can do, we can characterize depending on the parameters and the properties that whether it will be homogeneous or heterogeneous slurry. Okay, next let us see for heterogeneous slurry how to calculate the pressure drop. Already we have shown for homogeneous. So, we follow a model called 2-layer model. So, 2-layer why? Because you can see here we are having heterogeneous, means there will be some sort of deposition at the bottom of the pipeline bed. So, this is the solid bed, and here we are having more or less flowing slurry. Okay. So, we call this one as 2 separate sections. So, as it is having 2 separate sections, we are naming the velocity of this mixture as UM2 and UM1 respectively. Let us say this bed which has already settled is making 2 theta angle, okay, from the center of the pipeline. Okay. So, here you see this bed is actually contacting this S2 amount of arc of the pipeline, whereas the upper portion of the slurry is contacting S1 portion. Okay. So, little bit of geometrical analysis if we do, we can find out the contact length along the periphery by these 2 zones of the 2 layers of the slurry. So, what we can do, S1 we can write down pi minus theta into d, and S2 I can write down d into theta. Okay. Also, we can show that the area which is occupied by this upper layer of the slurry and lower layer of the slurry can be written as A1 into d square by 4 pi minus theta minus of sin theta cos theta, and A2 d square by 4 theta minus sin theta cos theta. Okay. So, all these things can be calculated from your geometrical configuration of the pipeline. We can also show that this line, which is nothing but the junction between both the layers, that is written as S12, the length of this line, can be written as d into sin theta. So, first whatever we will be showing is that contact load is alpha c. So, contact load alpha c can be defined as alpha S2 minus alpha S1 into A2 by A. Okay. All the parameters are known over here. So, we can find out contact load. Then for finding out the mixture velocity and pressure loss, you see mixture velocity UMA can be written as UM1A1 plus UM2 into A2. So, these are the velocities for the layers, okay, UM1 and UM2, and corresponding area I have already stated. Now, pressure drop, if we try to find out, then it will be tau 1 into S1 for the contact of the lower portion, and tau 2 into S2 for the contact of the upper portion, and then there will be a contact load called Fz. Okay. So, that will be coming into picture divided by A rho L into G. Now, contact load is something which one need to find out empirically. So, Shook and Rocco in 1991, he has given this expression for contact load. So, you see here everything is dependent on the value of alpha S1, alpha S2, which are the alpha different loading for 2 layers, as well as we are having theta as parameter. So, 2 theta is this angle. So, half of this one we need to take. Okay. Fc is very important over here. This is the friction factor for the contact load. So, usually we find out that Fc is in between 0.4 to 5.5. Okay. So, this is a model using which you can find out the contact load for the 2-layer model. Okay, let us summarize. In this lecture, we have described different flow regimes of solid liquid slurry flow. In homogeneous slurry, we have found out the pressure drop considering laminar, turbulent, considering Newtonian and non-Newtonian slurry, and finally for heterogeneous slurry using 2-layer model we have shown how pressure drop can be calculated. Okay. Let us test your understanding at the end of this lecture. First question, as velocity of carrier liquid increases, which regime conversion we observe? So, carrier liquid is increasing its velocity. So, first answer is homogeneous to heterogeneous, second one heterogeneous to homogeneous, third one moving bed to plug pipe, and fourth one moving bed to stationary bed. Okay. So, correct answer is part B, heterogeneous to homogeneous. Hope all of you have answered the correct one. Question number 2. So, volumetric flow rate of slurry is proportional to, so volumetric flow rate is V dot m is proportional to, we are having 4 answers, D, 1 by D, D square and D to the power 4. Okay. So, already we have shown the volumetric flow rate expression. So, you find out this is proportional to D to the power 4. So, last question, contact load in 2 layer model is proportional to, okay. So, you have to give the most appropriate answer amongst all the options. So, we are having alpha is 1, alpha is 2, alpha is 2 minus alpha is 1 and alpha is 2 plus alpha is 1. So, these alphas are different loading fractions for different solid layers, okay, in 2 layer model. So, I think all in the last slide, last slide I have shown you the correct answer, all of you have guessed. So, obviously the answer will be alpha is 2 minus alpha is 1. Okay, so with this understanding I will be ending this lecture. Thank you.